is question 19 from 6.3. And there are two questions here that I didn't cover. They're to do with expected loss, expected profit, which are questions C and D. We didn't cover it. I don't want to cover something I'm not going to do in the test. I've went back to the homework and I basically made these two questions worth 0 points, so you can ignore them. If you're interested in them, maybe what you do is you just find the percentage of times that you're going to fail multiplied by how much money that would cost the company, and then the percentage of times where it doesn't fail, and you multiply that by the premium that the company would get. And if you put those two together, and that ends up telling you the profit stroke loss. So we're forgetting those. Now, there is a story to do with a microchip, and it lasts for 92 months on average, and the standard deviation is 3.8 months. So this is, you know, one of those very reliable microchips, and it's put in, I think it was in the story, it was put in a satellite. And what they had to do here is that they wanted to know some percentages on how likely this thing was going to last you. So let's suppose the satellite had an expected lifespan of about 7 years. How likely is that going to work? So first question is, for how many months would it be so that you can 95% confident that it will last? So can you imagine that you've got your thing, right in the middle is the 92 months that it's going to work. And it has to last 84, right? And we're trying to find, eventually it has to last 84, and we're trying to find what number it would be that we would be 95% confident. What they're really telling us here is find this guy here so that that number represents 95%. Couldn't they have made this question simply, what is the 95th percentile? And that's what you would be getting. It wasn't phrased that way, but that's essentially what you've been asked to do. Now, we thankfully have a nice computer guy that does this. To get a 95th percentile, do we use the normal CDF or the inverse norm?
The normal CDF.
Right. So we are trying to find a number that gives us a 0.95. We're looking for an inverse norm. Right, percentiles, inverse norm. What percentage is less than somebody as it is here? Normal CDF, right? So here it goes. Inverse norm, 95%. Mean, 92. Standard deviation, 3.8. So hitting inverse norm here. And we have a 0.95 followed by a mean of 92 followed by a 3.8, and the answer that I have is about 98.3. Now, can you imagine this microchip is going to be on a satellite, and that satellite is going to be up in space, designed to last 84 months, right? They don't expect, no satellite lives forever, right? So they have a kind of, this is how long we're going to build it to last, and then we'll send up a new one. You are 95% of the time, isn't it going to last at least 98 months? So can you see that that's a good safety cushion? Right,
Probably
there's a net.
I don't want to answer, right?
Well, when I did the problem, they wanted it to be 98% confident, and I did inverse norm of
in
of
WebAssign,
yeah.
sorry, in WebAssign these numbers keep changing. In mine it was 95,
yeah,
right? So that's all that happened. Now when they did 98, that number will change, won't it? Marie?
Yes, but I put in inverse norm of 0.02 and then 92 and 3.8. And I got the right answer. I did the percent chunk.
Oh, you went over here
Yeah.
and you read it, is that way? I could have been wrong.
If we're taking the inverse norm, don't we want to take it as 0.05 instead of 0.95?
Well, that's what she was saying. My picture's got too much. Yeah. Either that bit is 95%, or they want this bit to be 95%. So I guess I should go back and read that question. If they wanted this version here, then she's quite right. And since that's the right answer, that is correct. Okay, so let's rephrase that question to be, whoops. I guess the moral of this story is read the question carefully. They wanted this piece here to be 95%, at least in the version I've got, and they wanted the little bit that's left over to be 9, to be the other 5. So that is going to be still an inverse norm. But in this story, it was that one. I want to finish this fella off to actually see whether or not that 84 is still safe. So if I go back to my calculator and I just change to the 0.5 version, I'm going to get, whoa, 85.8. That actually kind of makes sense. Would you agree that 84 is still safe? So yeah, that works well.
Well, question, if we put 84, would we consider getting it wrong, or putting the 85% would be better?
Now, this number is not a percent. This number is months. So it's 85.8 months.
Oh, well, months. I'm sorry.
Yeah. So 85.8 in this case. Now, if these numbers change, because I know that in some questions this won't be 95, it'll be 98 or 96, the answer is going to change accordingly. So I'm just doing one version of that question. So you may be looking at a slightly different number. I think Marie was saying hers was yours 98? Yeah. So if that's 98, won't this become 2%, in which case your question, this result here, which I'll write down again, this guy here, will depend on what numbers you use. So that's typical for WebAssign, that you get different versions of the same question. They basically keep the question the same, but they move the numbers around. Now, the second question, I think I got this right because it was very easy to write down. They wanted to know what percentage of the time you would get 84 or less. So if I did read that question correctly, I hope I have, then this is going to be a normal CDF. And what we would get here is that guy, and the mean is still 92, and the other guy is 3.8. And so I'm going to do a normal CDF on this one, and we'll see what we get. And the answer I get is 0.018, which is about 1.8% of the time. So that number there is what's the chances that the microchip actually doesn't make it for the full, in my story, 84 months, right? And the answer is really small, which is good because it doesn't guarantee that that satellite is going to be fine for its entire 84 months of usage. But isn't the chances that it breaks down before that time relatively small, 1.8? So I could imagine that they would probably be quite happy with that. If they wanted to be really sure, I guess, wouldn't they just have to make a better microchip that had even more stability and would take even longer before it would, in general, fail. One just side issue. Do you know when they do anything to do with spaceships that they tend to over-engineer it? So if something needs to last for 6 months, they try and engineer it so it lasts for 12, just in case it kind of fails earlier than it typically would. Mostly because when things in spaceships fail, people can die. And you know, when you've got a satellite that's worth $100 million, you really don't want it to fail because one screw wasn't quite as strong as it should be, and it breaks and something, you know, bad happens. So it wouldn't surprise me, I'm making this up, but it wouldn't surprise me if they use screws to screw down motherboards on satellites, that those screws are the best quality, most expensive screws in the world, that once you screw them in, they'll stay put no matter what you do. You know, that kind of over-engineering. And now we're about to start our last section for today. And this is what we need for this week. And we're going to look at again.
There's some stuff in the chat.
Oh, there is. Thank you for telling me. I'll go and have a look. I'll have to close this for a second because I can't see chat until that. Oh, okay. So someone is just sharing with us the fact that the engineers, I hope they want to share that. Where is it? Yeah, someone's husband is a mechanical engineer and they just built a chicken coop that could withstand a Category 3 hurricane. Yeah, engineers can do that. Oh, I've got to tell you a joke then. There was an engineer, a lawyer, and a mathematician went for a job. And so the mathematician goes in first and he's a little bit surprised. It was just one person sitting in the office on a table, and he sits down in the chair and the interviewer says, "Only have one question and the interview will be over." So the Scotsman says, "Okay, what's your question?" And he says, "What's 1 plus 1? The mathematician said, "It's 2. The guy says, "Are you sure?" He said, "Yeah, it's 2. It's always been 2. It's always going to be 2. It's 2. And the guy says, "Okay, that's it." And the interview's over. Scots guy leaves, kind of puzzled, and the statistician guy goes in next. Actually, an engineer, I should say, goes in next. And he gets the same question. And well, engineers aren't too bright, so he thought for a minute, and he says, "It's 2. And he looks up and says, "Are you sure?" And the engineer thinks for a minute and says, "Well, just to be absolutely sure, it's 2 plus or minus 1. Because that's kind of how engineers think, right?" And he leaves. And so the lawyer comes in next. And he sits down and the guy talks to him and says, "I only have one question. What's 1 plus 1? And the lawyer doesn't say a word. He gets out his seat. And he goes over and he checks that the door is closed, and he goes to the window and he brings down all the shades. And then he goes over to the interviewer and he whispers in his ear, "What do you want it to be equal to?"
I didn't get it.
Oh, come on. Lawyers don't care about the truth. They just want to know what their customer, what their person is, right?
Oh,
They don't care that you murdered someone because their job is to get you off, right? If a lawyer's job was to already convict you, it would kind of do a lot of damage to the criminal system, wouldn't it? You come in and you say, "Well, I'm in trial tomorrow," and the lawyer says, "Well, you did it, so what do you want me to do about it?" You know, I don't think you would keep them very long, would you? Right? So the joke behind that is that lawyers don't necessarily look at the truth. They look at what their client wants, right?
I'm going to have to share that one with my husband because he is an attorney. He's a lawyer.
Oh, Did you like that joke, Marie? I don't know if you could.
My dad's a engineer, so I get the engineer part.
Okay. The
but-
lawyer one wasn't so.
Not as relatable, but I think I got the joke though.
Okay.
Can I actually ask a quick question on number 19 that you were just going over?
Yes. What was the question?
Okay. I just want to double check. Is the reason you find the x, the value of x at 5%, is that because you're finding the value at which 5% the satellite will fail?
Yes.
Okay.
So the short answer was
Yeah.
yes.
Okay. I think that makes sense.
Okay. Well, I mean, there are two ways of looking at something. You can look at the chances that it doesn't fail or the chances that it does fail, and they are kind of connected, aren't they? Complements of one another.
Mm-hmm.
If something's got an 80% chance of failing, it's got a 20% chance of success.
Yeah.
Right. If it's got a 95% chance of success, it has a 5% chance of failure. So that question was geared to the failure percentage. So that's why it was that's why it was the 5% side and not the 95% side.
Okay.
So we are now going to be looking at what's called the central limit theorem. And I think I've got the screen on already. So where do I start? Okay. Let's suppose Bill Gates gives me lots of money. And he says, look, I don't care how much it costs. I want to know the average age of everybody in Washington State. I want to know their average age. And you say, okay, I am going to do a sample of 1,000 people. Oh, by the way, let's pretend that somehow the reality is known, just so I can do a comparison. Let's say the average age of the population of Washington was 30, right? So it would look something like this. Might not be quite symmetric, but basically it looks like that, right? Now, I take a sample of 1,000 people and I get their average age, right, the mean. Do you expect that that mean will come up with this real number, right, the true answer of 30? Would you expect just a random sample of 1,000 people, if I found the mean of them, it would be exactly 30? No. Would you expect it to be pretty close? Yeah, but not exactly it. So let's suppose I did it and it ended up being 31.1, because that could happen, right? Pretty close to 30. In fact, isn't that why we do samples? We assume that in general, if the sample's big enough, won't this answer be pretty close to that answer? I'd be really amazed if it was miles away, right? And that's fine. And Bill Gates says, okay, 31. Are you sure? Well, my answer is, well, I'm not really sure, because I couldn't have just had bad luck and get a bad sample for no reason except luck. I can't think of it. Where I just ended up asking a little bit more older people than I wanted. And so my answer could be a little bit further away than I expect. Probably won't happen very often, but it could, right? So I'm not sure. So I say, can I get some money? And he said, look, as much as you like. So you said, okay, I'm going to ask another 1,000 people. And I went out there and I got money. And I asked 1,000 people, right, or I paid somebody else to do it. And I get a second sample of 1,000. Do you think the second sample of 1,000 should come to 30? Exactly 30. Probably not. Should it be exactly the same as the first one even? There's no reason, right? It's a different group of 1,000 people. It might be 29.9, for instance. Agreed? So now I have two samples and they disagree with each other. Now they don't disagree with reality. Reality is 30, right? It's 30. That's what it really is. But can you see that these are a bit like trying to shoot a target, and sometimes you shoot the target and you're a little bit high, and sometimes you shoot the target and you're a little bit low. But if you keep shooting and shooting, don't you kind of get a clump of numbers that are kind of circulating around the right answer? So since Bill Gates gave me tons and tons of money, I decided to take all his money, almost all his money, and I did 500 different samples. God, do you imagine how much money that would cost? 500 samples of 1,000 people. And I found that when I got to the last one, wouldn't the last one just be as good or as bad as any of the other 499? There's no reason why my last sample of 1,000 would come out any more or less accurate than the others. And the last one I got was 30.7. And I've just decided to call the means X1 bar, X2 bar, X500 bar, right? So far, so good. Now, what the statisticians did is that they imagined that like a thought experiment, like you did it in general. Now, if you took all these guys here, right? And there's 500 different samples. You can create a sampling distribution. Now, can you imagine I had all these numbers, right? 38.1, 29.9, and so on. So I'd have 500 numbers. Can you imagine I got that? Couldn't I make a histogram of it? Right. All the answers that gave me 20 to 21, all the ones from 21 to 22, all the way up. If I did this histogram, you get what's called the sampling distribution. It would look something like this. And this is a little bit of theory, but it is true. If it was a perfect world, and I did this often enough, what number do you think the mean of this sampling distribution would be? This picture.
Wouldn't it be 30 now?
Yes. The theory says it should be 30, right? In practice, you know, nothing's perfect, but in the theory it says. So the mean of the sampling distribution will be equal to mu. Can you remember that mu is the letter that we use to represent the population mean? In a way, isn't that the property that we're using for why we do samples in the first place? Aren't we hoping that the one sample that we take, because typically we only take one, is going to be darn close to 30, because won't the average of all of them be 30? So you'd expect with a bit of luck to get that. Now, this fella here is called a really ugly symbol. It's mu with a little X bar on it. I don't like that notation, but that's what they're using in this book, so I'm living with it. That means the mean of the samples. So it's not one number, it's the mean of all these numbers. So if you think about it, this is a little bit weird. Aren't we finding the mean of a whole bunch of means? Right, that's what a sampling distribution is doing, right? It's taking a whole load of different means and we're finding the mean of them.
Yeah, but I mean, like, doesn't that logically make sense to like take the mean of several means in order to find a true mean?
Yeah.
As far as like populations go?
It kind of makes sense. It's kind of weird, but yeah, it makes sense. Agreed. Now, this bit might not be so obvious for you. The population mean is mu, right? And the population standard deviation is called sigma, right? This shape here, the sampling distribution, which is made up of all these numbers done like millions and millions of times kind of thing, so you get a perfect curve. This fella here also has a standard deviation, but it is not equal to the population's standard deviation. It's actually equal to that guy. And that's kind of magic, and there is a kind of proof that you'll never need to worry about, at least for this class. But that's the standard deviation of it. So let me explain why that would be the case. Can you imagine you're picking one person in Washington State and you're asking them their age? Just one person. Couldn't I pick a person and they ended up being 50 years old? Couldn't I get a person, you know, I said, hey, how old are you? Right? Totally random. How old are you? And the person said, I'm 50, right? If you took a sample of 500 people in Washington, can you imagine that it would be really, really difficult to get an average of 50 based on the fact that most, you know, the average age of a Washingtonian is 30, right? So wouldn't you get 20s and teens and 30s and 40s and maybe the odd 70 or 80? But wouldn't you expect it would be really quite hard to get an average of 50? So what's that telling me is that the original population has a lot of variation in it, right? Sigma can be quite big. But when you do a sample of 500, don't you kind of average out that variation? You shrink it down, and so it becomes smaller. And it becomes smaller by this formula, sigma over root n. So let's pretend that in Washington, the mean was 30. That's the population mean was 30. And that the standard deviation sigma was, let's say 15, just for argument's sake. Then the mean of my sampling distribution would also be 30, but wouldn't its standard deviation be 15 divided by the square root of 500, which is going to be a lot smaller than 15. 15 divided by the square root of 500. That ends up being 0.67, roughly. And the type of questions that at least we're going to do in this introductory section are going to be, what is the probability that you take a sample, maybe say size 1,000? And darn it, in space, I just made a mistake. N is 1,000. I was looking at the wrong digit when I did my scan. So what's the chances that you do a sample and its average is equal to any particular number? And that's the kind of things that we're going to be looking at. So let me use this guy. Right, so Washington, the mean is 30, the standard deviation is 15. What's the probability that I pick a sample of 1,000 people and I get a mean bigger than, say, 32? Right. So what percentage of the time would I end up getting a sample of a size greater than 32? Well, I know the mean of the thing, it's 30. And I know its standard deviation, which by the way is called that ugly guy. The mean is called that ugly guy. And I know this fella is sigma over square root of 1,000, which is 15 over the square root of 1,000. Kind of duplicate my work here, is 0.47. So if I imagine drawing this picture, this is what the sampling distribution would look like. Right in the middle, it would be 30. And then this kind of standard deviation. So this guy here would be about 30.47. This guy over here. Well, that's an awkward number, but can you imagine I did the others going the other way? How do we find what percentage of the data is greater than the number 32? That's a normal CDF. Right, there are going to be 4 numbers here. The last 2 numbers are the mean, which is 30, and the standard deviation, which in this case is 0.47. Right, there are 2 numbers to go now. In the usual way then, how do you find the chances something's bigger than 32? Where do you put the 32, the first or the second number? 32.
The
First or
first.
second? Anybody?
First.
The
Yes.
first.
And what's the magic number that I invented for the second one?
999.
Right? Now, I'm going to go, do you want me to do that in the calculator? Can I just, the screen calculator? Or can I just do it? 999. Can I do it on my own hand one and then that's a little bit quicker? Or do you want to see it being done on the screen?
Do it on the calculator.
Okay, so just do it on my own. Here it goes. Number 2, normal CDF. Typing that in. I'm going 32, comma, or bigger. 999 will do. A mean of 30, comma, and a standard deviation of 0.47. And the answer that I get is a ridiculously weird number. It's 1 e to the negative 5. That's tiny. That's 1 times 10 to the power of negative 5. That's what your calculator does when you go scientific notation on you. You done chemistry or physics, you should be used to scientific, tiny numbers like this. If I write this as a decimal, it's 0.12341. Even as a percentage, it's still tiny. The chances that you went to Washington State and you picked a sample of 1,000 people and you got a mean that was bigger than 32 would only happen once in a blue moon. Can you see how tiny that number is? Are we okay with that?
So what would that look like on the graph? Like putting it in percentage, like filling in the cake?
If you were writing that down in the box in your answer thing, you would write that guy.
I just meant like, what would it look like on the graph that you had drawn? Like,
oh, in the graph I've drawn, it would be
like where
a
would
tiny little number away over here.
I just wanted to make sure that's what I was thinking.
Oops, I'm wrong direction. Sorry, it's a tiny little number over here.
That's what I was thinking. I'm like, which way would it? Yeah.
32 is over here, right?
Got it.
And greater than 32 is this guy.
I'm just a visual person. I have to see everything and put it in place to put it there. Thanks.
Okay, so can you imagine then that you probably wouldn't see that very often, right? In the one sample that you took, the chances that you got a sample that is that big, a mean that's that big, would happen once in a blue moon. So it's not a big issue. Hopefully you wouldn't expect to see it a lot. But here's a different question. Suppose I pick one person from Washington State. What's the probability that that one person has an age bigger than 32? Now, it might look the same, but you see that's the mean is bigger than 32, and this is just one person. Would you agree it's a lot easier to pick one person being older than 32, right? If I said, how old are you? And they said what it is. Now, it's still a normal CDF, but bigger than 32 will be 32, 999. The mean is 30, but because it's a population and it comes from here, can you see that the answer is going to be 15? Or not the answer, but the number for the standard deviation is now the population standard deviation and not the sampling distributions standard deviation. You see that there's a big difference between these two. Now, when I plug this guy into my calculator, I should see quite a significant difference in what the result is. And the answer is, at least on my calculator, 0.447. Now, when you look at these two answers and you see how different they are, you might think visually, how can that possibly be true? Well, the reason why it can be true is, and I'm going to draw the picture in a minute, is that if I put this picture on top of that one, so you see both of them together, they have remarkably different shapes. this would be the population distribution. This would be, to scale, the sampling distribution. Do you see how it's very, very close to 30 almost most of the time? So can you imagine it goes maybe really skinny, really skinny, right? So can you imagine that when you get to this number over here, why there's so little left? But can you see in this question, why at 32, there is a lot left? Now, normally when we draw them, I draw them all the same shape. But technically speaking, can you see now that they're both together and one upon the other? Do you see that the shapes are quite significant? Can you see that this guy's standard deviation is tiny? I believe it was 0.47 tiny, right? And this guy's standard deviation was huge. Well, at least 30 times bigger, would you agree? Now, what does 30 times bigger look like? Well, if that's the first guy, won't the second guy be 30 times crunched? You can imagine taking this guy, right, and you're crunching its variation, standard deviation by 30. And so I don't get too lazy here. Sigma is 15, and sigma x bar is 0.47, because you're going to see that notation floating around, so you've got to be careful you know what they're saying. So if you see this, it's the standard deviation of the samples. If you see this, it's the standard deviation of the population. Are we good?
I have a question.
Significant contribution.
So can you explain why you entered the data on the left side of the page for the normal CDF in that last problem that you just entered? Just explain that again, because I didn't really catch that.
This one here?
Yes.
Right, so I'm looking for, from a population, one person, and we're trying to find what the chances are that that person is older than 32. So if you're thinking of the visual picture, there's 30, 32's about here roughly, and we're trying to find that guy.
Mm-hmm.
So I'm trying to do a normal CDF of 32 or bigger with a mean of 30 and a standard deviation of 15. So for this population, the mean is 30 and the standard deviation was 15. So that's where these two numbers came from. And bigger than 32 is where those two came from.
Okay.
So what's the chances of one person having an age greater than 32? This normal CDF will do that for you and ends up being about 44.7%. What's the chances the mean is greater than 32? It's also a normal CDF. Do you see the only difference is that the standard deviation is tiny compared to this one? And that's why this answer is so small. And correspondingly, that's why this answer is so big.
Okay.
So if we asked, instead of one person from Washington, if we said one person from the sample, it would be the standard.
Well, one person
deviation
from
of
the sample would, one person from the sample should probably be phrased as one sample.
Okay.
Because
Okay.
one person from the sample is one sample. Right?
Yeah,
It's,
that's true. It's
right.
the same thing. Got it. Yeah.
Agreed. Okay, let's do an IQ one, because you know I like IQ questions. Always have. Here's my little visual picture, IQ of 100. The population, well, the mean IQ is 100 and the standard deviation is 10. Let's find a kind of old-fashioned question, one we've done before. What's the probability that you get a person whose IQ is less than 99? So X means one person from the population and that their IQ is less than 99. Now, that's going to be a normal CDF. If you're doing less than 99, you have two numbers that go here, right? A mean of 100 and the standard deviation of 10. Okay, where does the 99 go when you're doing a less than 99 story? First or second?
Second.
Second.
Right, oh, there are going to be a lot of nines in this question. And what magic number do you put at the front when you do these kind of questions? Negative all the 9s. Can you remember less than was always negative 999, comma, the number, and greater than was always the number, comma, 999. It's basically you're going this way. Now, you might say, and it's true, but you can get an IQ of negative 999, and that's true. I'm not sure. I think you could get an IQ of 0 if you looked at the IQ test and never answered anything. That would probably get you 0, right? So you could have put 0 here. And the nice thing is that you get the exact same answer. I just do 999. That way you don't need to think of context. You don't need to say, well, what's the biggest number they've got in the test and finish at that? Or what's the smallest number it's going to be? If you use negative 999, it works for all of them, unless the number's huge. Now, on my calculator, that shouldn't be that unusual. Would you agree if that's halfway, which is 50, isn't the guy that we're going to pick darn close to 50%, right? I wonder what it is going to be then. In this case, it's negative 999 with a 99 and a 100 and a 10. And I'm getting about 46%. That seems reasonable, doesn't it? If you just pick one person at random and you find out an adult and you find out their IQ, the chances are that that person is an IQ, you could argue less than 99 or less than or equal to, it's essentially the same thing, is going to be 46% of the time. Almost half the people, which is kind of visually makes sense, right? That's almost 50%, isn't it? Same story. You take a sample of 100 people and you get their mean. What's the probability? What percentage of people would you get less than 99? I'm going to just do something here for a second. Okay, just to some background sound. Yeah, so now this is the mean. Now notice it looks almost the same, but it's a mean, right? So you did 100 people. What's the chances that this mean is less than 99? So can you imagine you asked 100 people and you averaged out what their IQ is? Now you're going to get a couple of 120s, right? But aren't you also going to get 85s and 86s? Don't they kind of balance out? The big ones tend to compensate the little ones most of the time. And so it should average out. There's the word average. Let's see what it is. I can tell you for sure, without even going near my calculator, won't it be a lot less than 46%? And let's see what it is. It's going to be negative 999, comma 99, comma 100, comma, oh, I better calculate the standard deviation of the sampling distribution. It's sigma over root n. It's going to be 10 over the square root of 100. Ah, made my life easy. It's 1. Right, 10 over 10, it's 1. And according to the calculator, the answer ends up being 0.159, which is 15.9% of the time. Can you see it's harder to move away from the mean of the population when you use a sample than it is if you just pick one person, right? To get one person at 99, it's going to happen a lot. To get an average of a sample to be less than 99, do you see it's much smaller? Now, if I went down even just a little bit more, like, what's the chance that you pick one person and the answer is 90? That'll still be a reasonably big number, right? There's a fair chunk of the population that's true for. Do you know if I did it to this fella? You'd get one of those 0.0001 kind of things, right? It would be tiny. In other words, it's extremely unlikely to happen. I'm going to change tack a little bit.
I have a quick question.
Yes.
On the, this isn't super important, but on
Go for
the
it.
X is less than 99, I actually got 0.496.
I'll just check that I didn't go and.
Okay.
Did everybody else get 496? It could well have happened. I could have scanned it and missed a 9. Which case?
Got 0.4602.
Oh, okay then. Let's just do that.
Marie, oh, sorry. She left the standard deviation is 10, not 1.
Oh, no, that wouldn't. Well, that may have been a mistake, but I don't think that was her mistake. I think if it is a mistake at all, it was just typing in something else, I suspect. Right, I'm going to put this one in and we'll just do a quick check. So you know me, it's very, I'm more likely to have made a mistake than anyone else, you know how careless I am. We have this fella. The number should be -999, so I'll put that in. And then I'll do a comma, and then, oh, it was 99. Then I'll do a comma, and we're doing 100 and a 10. So there's 100, and there's the 10.
Oh, wait. I think I might know what I did.
That's okay.
Yeah, I'll try something quick. There, now I got it. Yeah, thank you.
No problem. I'd rather you tell me that I'm wrong and then occasionally I get lucky and I got it right, than to let me be wrong and let it slide, because then you go back and you look at your notes and then you start, you know, second guessing yourself. Well, if that's right, why am I not getting the number he wrote down? Because you might go back and try it yourself on your calculator, and it's worth it. It's worth it as a backup. Now, let's look at it's kind of looking forward a little bit, but just to give you a kind of context to this, you know that in real life you only typically do one sample, and that one sample is all you've got to play with, right? So let's pretend that I took a sample of 10,000, which is a massive sample, right? That'll cost you money.
We can't see your white screen.
Oh, I gotcha. Right. So imagine, I'm going to go through this in a second here, that I did a massive sample of 10,000 people, and the mean age of Washingtonians was 30.5, right? Or some other state, right? Let's just pretend it's a new story, right? So the mean age of Wisconsin is 30.5, right? And let's say, which is highly unrealistic, but let's say that I somehow know that the standard deviation of the population was 15. Now, I know that the mean will probably be close to 30.5. So if I draw my guy, there's 30.5, right? I know that the standard, the standard deviation of my sampling distribution, which is sigma over root n, which is 15 divided by that big number, which is 0.15. Now, if I build a little sampling distribution, as I have here, the mean is 30.5, the standard deviation is 0.15, and there's my 3 little marks. Won't this fella here be 30.65? Won't this guy be 30.8? And won't this guy at the end, 30.8, and won't this guy at the end be 30.95? And if I go backwards, so hopefully I'll do this right for a change, you'll get 30.35. You go back a little bit further, you get 30.2. and then you get 30.05. Wouldn't that represent the typical shape for a mean of 30.5 and a standard deviation of 0.15? Now, if I do 2 standard deviations either side of this mean, I get the numbers 30.2 and I finish at 30.8. What percentage of the time do you get within 2 standard deviations of the mean? That's a guy we did a way back.
Is it 95?
It is. Now I can say this. I am 95% confident that the mean of the population is somewhere in the range 30.2 to 30.8. I can write it as 30.5, give or take 2 standard deviations, give or take 0.3. What I've done here is I'm not just telling you what my best guess for the average is in Wisconsin, which is my sample size is 30.5. Aren't I giving you a little wiggle room and saying, look, I'm 95% sure that the right answer is somewhere in this range? Doesn't that give you some idea of how accurate an estimate I have given you? That it's that number, give or take a little, right? Suppose I did the same kind of sample, but a different size sample. And I said to you, it was 30.5, give or take 10 years. Can you see that it's not as useful to know that the average age of someone in Wisconsin is somewhere between 20 and 40? Isn't it much more helpful to know it's somewhere in the 30s? Now, how does that happen and this happens? Well, this happened when you have a really big sample. This happens when you have tiny samples. Why does tiny samples make this happen? When you go up here, aren't you going to divide by a very small number, like 80? Won't this become really big? And if this becomes really big, won't 2 standard deviations become really big? So the bottom line is, if you want to get a good predictor on anything, shouldn't you get the biggest sample you can afford? Because what it will do is it will give you an answer that you'll be able to do this kind of calculation to and put what you might call a tolerance on it. It actually has its own name. Do you know this little bit here? It's made up of 3 words that you might have heard on the news.
Is it margin of error?
It's called the margin of error. You ever heard them? It tends to be done with percentages, but it can be done with this as well. The percentage you're going to vote Democrat in the latest poll is 51%, and the margin of error is 3%. So what they're saying there is 51 plus or minus 3%. And that is only a 95% confidence. It's called a confidence interval, as you'll find later. Do you notice it's a 95% confident? I'm not 100%. And you're never, ever going to be 100%. Isn't there always a chance that you did everything right and Murphy's Law screw up with you? And you just happen to ask a lot more old people than you know, in randomness you should have, right? Just bad luck, right? You know, some people can gamble and win all the time. Some people can gamble and lose all the time. Isn't it, for want of a better word, I'm lucky and he's not kind of thing, right? That's why we never, in statistics, say, we know for sure that it's definitely in this range. What we say instead is, I'm 90% confident, or I'm 95% confident, and the third one we typically use is I'm 99% confident. If you turn that story on its head, isn't there a 5% chance that this answer isn't even anywhere near the real answer? I just got a bad set of data, right? Because 95% confident means I have a 5% chance of being wrong. And being wrong means anything. It could be a lot bigger. You know, it could be a way over here in the 30 odds or 40s. Could be a lot younger, right? Could be a way over here in the 20s. You don't know. When you're wrong, you don't know what you're wrong by. You just know it's not the answer you've got in front of you. So obviously, isn't a 99% confidence probably a better measure if you want to be more sure? What do you think would happen to this interval, the size of this interval, if I moved to what would be a 99% confidence? That's roughly 3 standard deviations away from the mean, very roughly. Wouldn't they get bigger? Because a bigger interval, I'm more likely to have caught the right answer in it. So what we're looking at here, this is the beginnings of how to take just a simple sample and get as much info out as it can. Now, I'm not just going to say, my best guess at the average age of Wisconsin is 30.5. Right, I'm not going to say that anymore. I'm going to say it's 30.5, give or take a margin of error. And doesn't that help a little bit more? And now I'm going to contradict myself. I said you can never be 100% confident, right? So here's an example of me being 100% sure. The average age of someone in Wisconsin is 100 plus or minus 100. Would you agree the average age of someone in Wisconsin is somewhere between 0 and 200? Would you also agree it's a pretty useless piece of information? It's a bit like somebody who doesn't know math and says, well, if I answer every numerical question by just saying it's somewhere between negative infinity and plus infinity, it is correct. It's also totally useless, isn't it? So we are always fighting how confident we want to be, with the fact that if we want to be really confident, couldn't we get to the point where the interval we give you is pretty useless to use? If I went and said, I did a 99% confidence on who's going to vote Democrat, and the answer I get is somewhere between 20 and 80%, doesn't that mean, oh, well, nobody knows who's going to win then? I'm 99% sure I got the right answer, but my interval is so useless that I'm not going to be able to do much with it. So you're going to have to balance risk of being wrong with usefulness of the answer. Because if you want to be really sure, the interval gets big, and big intervals tend to become more and more useless the bigger they get. And if I wanted to make that interval smaller, then maybe I'll have to do a 90% confidence, right? Which means 10% of the time I'm going to get it wrong. The going rate, as far as I know, and I'm not 100% sure, because they don't normally share, when Gallup poll do things like this, they don't normally share what confidence interval they're using. So see when they say 42% and the margin of error is 5, I don't know, for instance, is that I'm 90% confident it's in that region, or I'm 95, or I'm 99? And secondly, I don't even know how many people they asked. And so that's why you could have, quite easily, couldn't you have 3 different polls with maybe not hugely different answers, but different answers, different intervals of where the real truth is? And they're not cheating, they're not lying. Couldn't it be, I'm doing a 99, so my interval's really big because of that. So my margin of error is plus or minus 6%. You know, and somebody else is doing, oh, I'm only going to be 90% sure. If you do a 90% confidence interval, and you did it to every single state in America after the elections, right? If you're doing your forecasts, and you use a 90% confidence interval, doesn't that mean you're going to get 5 states wrong? Right, 10%. So you're going to predict Washington goes Democrat and it goes Republican, or Texas goes Republican and it goes Democrat, right? You're going to do that. And because you're using a 90% confidence, which means 10% of the time it's going to be wrong, you're going to come up with results that don't match. And people get annoyed by that when there's a prediction that Florida is going to go independent and a Republican wins. And people says, well, you went and predicted it was going to go, and it went Republican, voter fraud, and all the stories that it's attached. And very often it's nothing to do with voter fraud, isn't it? Just they were one of the 10% that they got wrong. That's all it means. And so don't try and put motivation to situations like that, because they do happen, right? I would put much bigger skepticism when the poll is conducted by a group of people who have a political affiliation. So if a pro-abortion group was doing a poll on who's going to vote, don't be surprised if that tends to favor Democrats. And if an anti-abortion group pays for a poll, don't be surprised if that favors Republicans. Now, that doesn't mean every Democrat is pro-abortion or anti-abortion, but actually, if you look at the detail, if you delve in, there is a discrepancy, right? More Republicans are anti-abortion than they're pro-abortion, and more Democrats are pro-abortion than anti. Now, it doesn't mean that you should change your party because of that. It just means that's life, right? And so when you ask, if you ask pro-abortion people who you're going to vote for, don't be surprised if there's a lot of Democrats in it, right? And if you ask a lot of anti-abortion people who you're going to vote for, don't be surprised if there's a lot of Republican voters in that group, right? That would be, I guess, my bottom line. Are we good?
Yeah, I have a quick question.
Yeah.
The textbook said that the y-axis of a sampling distribution is relative frequency.
Yeah.
Do we need to know about that?
Not really, it just tells you the
Okay.
scale of the thing. Oh, I'll give you an example. Remember that weird picture I did? Where the population went like this, right? And the sampling distribution looked like that.
Yeah.
You know, from here to here, the whole thing adds up to 1. So if you were doing the vertical scale, that guy there might be 0.2 because there's a big width here and the whole thing adds up. You can imagine this guy here might have a high of 0.7, but the width is quite small.
Mhm.
And that's why this has an area of 1 and that has an area of 1. So you don't, yeah, actually my scales are wrong, aren't they? But you get the gist of it.
Is that specific to sampling distributions?
No,
that
it's true for
the
all
y-axis
populations.
is.
Yeah, the y-axis represents the relative frequency. You can also say it represents the probability, because those two terms are interchangeable. Oh, and while we're talking about things that are interchangeable, can you remember that that guy is the standard deviation of the sampling distribution? You will also find that it's called the standard error.
Okay.
It's still the same guy, it's just got a different name, right? So if you hear the question, it says the standard error is 4. They've already told you what that is, so you don't need to do a calculation on it.
Okay, but for sampling distributions, the y-axis
Is a
it like
relative frequency.
Okay, that's special to sampling distributions?
No.
Or,
The y-axis is the same in both cases.
okay.
It represents the percentage of time you would expect a number in that general area.
Okay.
Okay. If you do integration in Calc 2, essentially the area under this curve is 1. and this would the y value would represent the height of the function at that point.
Okay, so it's specific to all population distributions that the y-axis is.
Yeah, they're both they're both for they both represent relative frequencies in both situations. So I am going to nip over, if I can, really quickly. Anybody in chat? Oh, you are right. Pro-women's right to choose. I should have used those phrases, didn't I? Say pro. No, I think I was neutral. Is pro-abortion and anti-abortion neutral?
I think no one is pro-abortion. I think they're pro the ability to get an abortion.
Okay, so that isn't neutral. You're right. I should have said if you do people who are pro-choice and pro-life, in which case I would be biased in both directions, and that would equal out the biasness, right? Yeah, you're right. Anti-abortion. You're not pro-abortion.
No, nobody's advocating for abortion. Nobody's out there saying more abortion now. They're just advocating for people's ability to get.
Yeah, I guess. Yeah, yeah. I can't argue. That makes sense. I'm just thinking what the neutral version of that sentence would have to be, and it's hard in my brain now to figure a different way of saying it.
Reproductive rights.
Say that again.
Reproductive rights.
Pro-reproductive rights and anti-reproductive rights, but then wouldn't the anti-abortion people disagree with that? Yeah, that's a really, God, that's a dangerous place that I'm going to here. Here's what my brain is telling me, and my wife would say, stop talking right now, Donald, but it's too late, it's coming up. Most people are neither 100% A or 100% B. It's much more of a spectrum, right? So most people who are anti-abortion, right? Right. Almost every single one of them, there are situations that they would understand, at least we'll use that word, they would understand why an abortion might be necessary. Can you imagine the woman could die in childbirth? That might be a problem, right? I mean, most people, even if they're extreme one, do see situations. People who are pro-choice, there are situations I'll create one that I think they might agree with me. Suppose a woman could take, because we give it to her free, the pill and not become pregnant, but she chooses to have babies and then aborts them, and continues to choose to have babies, to get pregnant at least, and abort them. Most people who are pro-choice would consider that a bad choice. Would you agree? That's not the way that you should do birth control. Get pregnant and then abort the thing, right? That is not what I think most of the people who are oh, I've forgotten the word there, right? But you know, those women who are looking at, am I in a hole already?
Oh yeah.
Oh God, I'm in a hole. Okay.
No, you're
I'm
not.
just trying to say that virtually nobody is 100% anything on the abortion situation. There, I could say the word situation, right? Nobody's 100%. Can you imagine there are circumstances that people who are strongly in one favor might see a reason for why you might want to do it, and people on the other side could imagine situations where that would be a bad idea to do birth control, right? So nobody is one or the other. So yeah, they're not all going to say, yeah, let's have abortions all the time, right? I understand that. That'd be quite offensive to them, right? But can you imagine that there could be situations that you might say to a woman, look, that's probably not the best way to, to do birth control, right? There's better ways, not just for your own body, because abortions are horrendously, could be dangerous, especially if you do more than one of them. So have I dug myself sufficiently out of that hole not to get a reprimand from my boss? If I've offended anyone, I truly apologize.
Okay.
I wasn't meaning to.
You're okay. You didn't offend anybody.
You're fine.
We're good? Okay. Dodged the bullet there. You know, I should just listen to my wife's voice when she says, stop talking, Donald. This is not going to end well. I've got to have to share this with you now. It's in my brain. to give you an example of why that's a very good piece of advice, I don't think I told you this story, and if I did, well, I'm telling you again. I was at a bank once, and the woman was the other side, and the woman was quite large at the front. And I said the dreaded, "When's the baby due?" Yeah, I did. And she wasn't pregnant, and there wasn't a hole deep enough. And I was just thinking to myself, God, Donald, you're dumb.
It happens. It happens.
It happens. So, right. So, will you give me a bit of sympathy in the future if I stick myself in a hole somewhere?
We know you have good intentions. It's all
even
good.
I have good intentions, I can screw up, right? And I certainly had a kind of, the anti-abortion one is kind of in that vein, right? I didn't mean anything by it, it just came out badly. Okay, so where are we? God, I've lost the place here. I've totally lost the place here. Can wait a few moments while I gather my thoughts and find the homework that I'm trying to find. Oh, good, I have found it. Right. It was there all the time.
Hey, Professor, I have a question.
Go for it. Nothing about abortion, please.
Will the recordings of the lectures for this week be up on Canvas? I just
They
wanted
will eventually be, and glad that you told me that. The grading has taken me a lot longer than I hoped. So I haven't got your class done yet, but my goal with the time I've got is to get the grades done first. So that's why the Zoom lessons are not up online. But the minute I've got the last class graded, and your class is actually going to be the one I'm going to start grading as soon as this class finishes. So hopefully I'll get yours online in about 2 or 3 hours, probably 3 hours. Once I've got the last class graded, I'll start putting them online. So you might not get to see them until Friday, more likely Saturday, because although you don't know it, those videos take a long time. And most of it is sitting waiting, because when I do the editing, it takes about an hour and a half, because I've got really crappy computer, and it takes that. And you know, I then have to upload it to YouTube, and you know, that takes another. And then you have to, the copying is actually the easiest part. Once it's in YouTube, it's pretty quick. But typically it'll take me about 2 and 2.5 hours to upload a Zoom lesson, most of which time I can go and watch the movies or whatever. But, you know, it takes time. And then I can't do the next one until the next one. So it kind of, you know, whatever I'm trying to say is it just takes a long time.
Yeah, whatever you
But
get.
I will get them up. But my priority is you want your scores first, right? You want that before you want your Zoom lesson.
Yeah,
so are we all looking at the questions from section 6.5, which is what you need to get done today? What you need to get done by Sunday. The first ones I'm going to go through, probably tell you most of the answers. They're just multiple choice. It's not like they'll take you long. First one is, oh, I'm glad I did this. What is a standard error? Well, it's a sum of a sampling distribution.
Is it the mean?
Standard deviation.
It's a standard deviation. Remember I said the standard deviation is called, its other name is standard error. Right, now this one I'll try to put into English. They're talking about two, so there's two answers to be found here. Unbiased estimators of their corresponding parameters, right? Now, an unbiased estimator is like a sample where you do a calculation and it's being used to estimate something in the population. So I'll give you an example of one of those. Isn't the sample mean, and let's use the word a good estimator. Isn't the sample mean a good estimator for the population mean mu? Imagine I decided to estimate the mean of a population from a sample. And the way I decided to do it was, I was only going to take the biggest number in my sample, subtract the smallest number in my sample, and divide it by 2. And I figured out that's a good estimate. Can you imagine that wouldn't be a very accurate estimate? That would be a biased estimate, right? It wouldn't typically give me a good result. Now, This guy, oops, wrong one, meant to hit, there's my scanning. This guy is the other one. And I still can't hit the right answer. I did hit 3 by correct, but it's actually the fourth one. It's P hat is an unbiased estimator of P. We haven't done them yet, which is a little bit strange because this stuff has still to happen. But do you know that we're going to do samples where we don't ask people their age, we just ask them who they're going to vote for? And the answer you get back is 45% of my sample are going to vote Republican, right? That kind of question. That's called P hat. P hat is the percentage of people in your sample who said yes to whatever question you asked them. So if you said, are you going to vote Democrat? And they said yes, P hat would be the percentage of people who are going to vote Democrat. P is the population number, which is how many Democrat voters are there going to be in America, right? So you only asked 1,000 people, but you got an estimate for what the true answer is. What happens to the, sorry.
Can you say, what does the bias mean again?
Bias just means if an estimator is biased, it doesn't home in on the number you want it to home in, right?
Oh, okay, okay.
It's a number that's not good at calculating the thing you're trying to estimate, right?
Oh, that makes sense.
Right. I think it gets the analogy from, can you imagine the bullseye is what you're trying to get? And you have an estimator that tends to be quite close to it. That would be an unbiased estimator. But can you imagine an estimator that you always are on the outer right? The numbers you get are miles away from it, and no matter what you do, you're never going to kind of get it. Or can you imagine they're always too far to the right? So you're not shooting at the bullseye, but you're shooting 4 inches to the right of the bullseye. Those would be examples of biased estimators. Now, variability. You know, variability is how spread out the data is. So describe the variability of a distribution, how it changes as the sample size increases. So as the sample size increases, what happens to the variability?
It gets smaller.
And that's that one. And I just recognized my first question. If you are looking at how big should my sample be to be at least reasonably close to the right answer, let's do silly. Could I do a sample size of 2? Sure. Would a sample size of 2 get you a very good estimate of the mean if you only used it once? Could be anywhere, couldn't it? 2 numbers could be anything, right? You could pick 2 20-year-olds, 2 50-year-olds. Samples have to be reasonably big. If the distribution that it comes from isn't perfectly normal, then your sample size has to be bigger than or equal to 30. And that's just a magic number that statisticians have figured out is a good rule of thumb. So what it's saying is, try and at least make your sample 30 to be safe, right? Anything smaller, there's too many chances of weird things happening, right? Even 30 is kind of small. You could have rather 3,000 or 300, but sometimes that costs too much. Now, on the other hand, see if your original data, the X's, came from a normal distribution. Technically speaking, any size will do. But I still wouldn't use a size of 2, but that's for practical purposes. In question 5 here, consider 2 samples, right? 2 samples corresponding the same X distribution. The first sample is based on a sample size of 100, and the second is based on a sample size of 225. So you imagine I took one sample and I only picked 100 people and I asked them, and I took a second, they 225. which one of these would have the smallest standard deviation? Remember, standard error is just another name for the standard deviation of the sampling distribution, right? Which one of these, a 222 sample, would have a smaller, or the 100?
$225.
Yeah, isn't it true? The bigger the sample, the smaller the standard deviation is, the smaller the standard error would be. Okay, then it goes on and it explains the answer. I'll let you figure that out. It's basically just picking whichever one of them makes the most sense. And here we are entering some algebra. So I'm going to have to zoom out here for a minute and show you how to do it. In this question, you know the sigma, and that's the population standard deviation, is 40. And you're being asked to find the standard error. Oh, SE, standard error, that's good. Standard error, right? Which is this fella. And you're being asked to make it so that the standard error is 2. So the guy that's doing the experiment says, I want my, basically the standard deviation of my distribution, my sampling distribution, I want it to be 2. I don't want it to be any bigger. How large should my sample be? Can you see that you've got a little bit of algebra here? One of the few places in statistics where we get to solve equations. So here goes. What should I do in the next line? And does this help?
40 over square root.
Oh. Correct. What should I do after that?
Get n by itself. So
correct.
Multiply 40, right? To both sides.
Cross multiply, essentially the same thing. Agreed? Now, what do I do to both sides to find the square root of n on its line?
Divide by 2.
Now, here is the last step. For some reason, unfortunately, people make a mistake here. Getting all the way to the end and then screwing up, unfortunately. Do you know that n is not the square root of 20? That's the mistake they make. They think it is. What do you do to both sides to get n?
You square them.
Yeah. So you need a sample size of 400. If you're going to do a sample on this population with this particular standard deviation, and you want to make sure that your, the sampling distribution standard error happens to be just be 2, right? Then you're going to have to pick a sample of 400. Now, what's going to happen in the second question when they said we want it to be 1? Oops, so it's going to be 40 over root n equals 1. And that's going to be 40 is the square root of n, and that's going to be 1600 is n. Wow. There's something you might not have expected. If this is basically the standard deviation and it's 2, you need 400 people to get that kind of standard deviation. If you want to half it, right, so going from a standard deviation of 2 to a standard error of 1, and I'm using the word standard deviation and standard error interchangeably here. If you go from 2 to 1, isn't that halving the standard deviation? You might have thought that you only needed to double that to 800. Do you notice that you have to increase it to 1600? Which is what, actually 4 times as much, isn't it? What that tells us quite easily is that, if you want to make this number really small, if somebody says, I would like it to be tiny so that when I write down my answer, it'll be a really, really tiny interval, right? Do you know when you do that, this number becomes so big you probably couldn't afford to do the survey. It wouldn't surprise me at all if this answer here, for instance, ended up being 160,000, which is actually what I believe it is. Now, can you imagine how much money it would cost to do that? So there is a balance. It's called like the law of diminishing returns. It costs a lot more money to get this more accurate. In the usual Gallup poll world, do you know what the going rate for a normal sample is? How many they typically ask? I'm assuming that's what their normal rate is when people come and ask them to do surveys for them. Any guesses what it might be? Last chance, any guesses? It's just over 1,000. It's 1,024, 1,016, 1,000 and something. And you might think, why is it not just 1,000? Because that's a nice round number. Why is it 1,026 or 1,024? It's really practical purposes. They actually only want 1,000, but they always pick 20 odd more because of non-responders. Some people just don't want to answer. And so they have a little backup, right? So they can lose a few names and it won't matter. Now, we're almost done for today. This is how they are going to phrase the questions that we spent today doing, the population of Wisconsin, right? So you're going to get a population of 22 mean and a population standard deviation of 14. And then they're going to talk about a sample, in this case, 33. And you're going to be asked to find these two guys first and then find that. So in this question here, won't this number be the population number 22? This number here, which is the standard error, that's one of its names, it's not 14. Isn't it 14 divided by the square root of 33? And so I'll do that on my calculator. So 14 divided by the square root of 33. And this answer, well, God, 4 decimal places, they are being a pain. Okay, so here goes 2.4371. Hey. Now, how are you going to do this, guy? Isn't this going to be a normal CDF? 20, oh, darn it, there's too much variable going on there. I am going to be zooming over to my little guy in a minute. And showing you rather than saying it. Okay, that was the population mean, but it's also the sample mean, right? Sample distribution mean. Isn't this guy, it was calculated by doing this fella, right? Which happened to be, oh darn it, I didn't write down what sigma was. It was 14. So it was 14 over the square root of 33. Now, if you want to get this guy, won't it be a normal CDF? That's kind of what we did at the start of today. 22, 24, 22, because that's what the mean is, and standard deviation of 2.4371. Are you happy about 22 to 24, where that came from? The mean, which is 22, and the standard error is that guy. So I then go to my calculator, and I go second distribution, this fella here, I go 22, 24, okay, 22, 2.4, 371. And hopefully I did the right thing. And I'm looking at 0.294. So I'm looking at 29.4%. So the chances that you get a sample from this population here, using a sample size of what, 33, the chances that you get a mean between these two numbers is going to happen about 29.4% of the time. And can you imagine they're going to have versions X bar bigger than 15, X bar less than 27. And wouldn't you do normal CDFs for those as well? Does that make sense? It's just the way they phrase the question. It's still what I've done. It might not look like it until you get in the workings of it. And oh, yeah, I've done that.
And how did you know that the N was 33? Was that given?
And it was in the story, yeah. It said the sample size was 33. And the same reason I knew that was 22, because the story told me it was 22, and the story told me that was 14. There is one other version of that question that you can get, and it is the kind of question that goes like, what X bar would you get in the, let's say, the top 30%? I'm just phrasing it that way. Now, can you imagine your sampling distribution? If you're in the top 30%, aren't you over here? And we need to find this guy. But if you're in the top 30%, doesn't that also mean that you're the 70th percentile? So when you deal with percentiles, it's inverse norm, 70%. The mean is still 22, and the standard error is 2.4371. I will do this one, and inverse norm 0.7, 22, 2.4371, and the answer I get is that the mean number would have to be about 23.2780, which is ridiculously accurate. And the reason why it has to be is, in this group of questions, didn't they ask for the answer to be 4 decimal places? And I just realized I wrote that to 3. And so 4 decimal places, I know what the last digit is. Can we pretend it's a 3 or something? And you would have to write 4. Because if you write this down and it's not got 4 places to it, do you know the calculator is going to, the software is going to say you're wrong? When really you were right, you just didn't write it to the accuracy they wanted. So all answers are as decimals instead of percentages. That seems to be the going rate. And when it's X bar, it's just obviously the number that you get. Whew, we made it. A bit rushed at the end, but I think we got there. And everyone has sometime today is going to be looking at their email. And there's 2 things. God, I am slow. Number 1 is I am going to take today's attendance. So if you hold off, I'll give you a few speckings. If you want to smile, you can. Otherwise, we are good. And I have now grabbed some smiling faces for a change. That's that done. There's one last thing. This truly is my last thing. I'm going to go and load up my spreadsheet with your data on it. And I want to check that the numbers I've got for your participation are the same as before. And okay, so Kelsey Alvarez, are you here?
Yes, I am.
I have perfect, is that right?
Yeah.
We agree. Rachel Ayers, are you here?
Yes,
I have you missed 1. Does that sound right?
that's right.
Okay. Doris Bates, I got you missed 1. Are you here? Right. Cody Bragg, are you here?
Yep.
I don't have anything yet on you. How many days have you missed so far,
None.
if any? None? Is that
Yep.
what you said?
Correct.
Oh, good.
Correct.
Right. I look at your pictures, and as long as we agree by one, I'm picking your answer. I look at the scans, but I know that sometimes like right now, I did it so late that you were here, but you had to go to another class and I missed you. So that's fine. Brittany Carroll, are you here? Cassie Clark, are you here?
Yes.
Okay. Okay. I have 2 missing. Does that sound accurate?
I think I was just late to 2.
Then I'll give you that. You are now there. Okay. Erica C, are you here?
Yep, I'm here.
I get a full. Actually, I don't need to ask you if you're a full, because I doubt if I think you've been here 11 times, even if you think you've only been here 10, I'm right and you're wrong. So I'm skipping by the 11. So if your name's not mentioned, it's because you're perfect. Jennifer F, are you here? Miss one?
Yeah.
We agree. Okay. It's not going to matter in the long run because you get 3 freebies, but that won't happen until the end. Jenny G, are you here?
Nope.
I have missing 1.
No, I haven't missed any.
Okay, then I'll take that as you were late for 1, or I just didn't copy it at the right time. Shukriya, are you here? Okay, move on. Tomoko, are you here?
Yes,
What do you have? Did you miss any days?
I late one time, but I didn't miss anything.
Okay, late's not really an issue, because sometimes I'm late as well, as long as it's not 2 hours late. Gracie H, are you here? Okay, we'll move on. Is Angelina here? Move on. Shoko K, are you here?
Yes.
I have 1 missing.
Mhm.
Okay. Cynthia, are you here? Cynthia? Okay, move on. Couple of people perfect, so I won't ask you. Moshe, are you here? Okay,
Yes.
then I'll just. Okay, I have 1 missing.
Yeah.
Okay, next is Emily.
I'm here.
I have 2 missing. Does that look accurate?
Yeah.
Okay. Shay, you here?
Yes.
I have 2 missing. Does that sound right?
Yes.
Okay. Genevieve, you here? Genevieve? Okay. Zoe, you here?
Yep.
Okay, Zoe, how many have you missed, if any?
I haven't missed any, but I had trouble logging into one, so I was late.
Yeah, you can't help that. That's fine. Jenny Weaver, you here?
Oh, I thought you already asked me.
Oh, you're right. Okay.
Professor, you said if you didn't call our name that we're good still, right?
Yeah.
I just want to make sure because
You're good. That means you got 11.
All right, perfect.
Ellie,
Sweet, thank you.
You're welcome. Bye-bye. Ellie,
Yes.
are you here?
Yep.
I have missed 2.
I missed 1.
Missed 1.
Yep.
Okay, I'll fix that. Ellie, oops, God, I put that in the wrong place, didn't I? Okay, put it in the right place. That should be everybody. We all good? Right, I'll hang about for 5 minutes because there may be some questions. Otherwise, I'll see you on Monday. If you get stuck on anything, or maybe I didn't cover it to the detail you needed, the usual, shoot me an email.
Thank you.
Bye-bye, guys.
Thank you.
Bye.
Bye-bye. You're welcome.
I just have a quick question.
Right, hold that thought for a second. I just realized something. I better save that file. Otherwise, all those checks disappear. Right, now I'm good. What was your question?
So yesterday I wasn't here for a doctor's appointment.
Yeah.
And I was wondering, was that Zoom meeting recorded? And
It's
will that
been
end up-
recorded. Yeah, it's been recorded, but you won't get to see it until Friday or Saturday because I haven't put it online yet.
Awesome, thank you.
You're welcome. Okay, we got Jenny and we got Marie. Who's got a question?
I have a few questions. So, Jenny, you can go first.
You're going first, Jenny. Go for it.
Okay, I have kind of a question that has to do with sort of anecdotal, just real life statistical things.
Okay, go for it.
Like, say, for example, I was extremely talented in writing when I was younger. I'm an author,
Okay.
but now becoming a nurse. But I was always did really well on the tests, the standardized tests, and they'd say, you are in the 99th percentile.
Cool.
Why was I never in the 100th percentile? Does the 100th percentile exist?
To be the 100th percentile, you would have to be the one person in America or whoever took the test, that one person who got a higher score than anyone else.
And so does that exist? Like, will they?
Yeah, I can. Yes, it would exist. Can you imagine that we did IQs for everybody in Olympic College, and we did really accurate IQs, right? So we got really good data on it, right? Wouldn't one person in OC have a higher IQ than anyone else, or at least a draw? Maybe two people with the same high IQ. They would be the 100th percentile people for our restricted population. There are anecdotal things that are depressing. Do you know that half the people are below average in everything? Do you know half of you are below average height, typically? Half of you are below average IQ, half of you are below average wealth, half of you are below average, insert a year. And it's not that it's a bad thing, but isn't an average, if we think of it as a symmetric distribution, isn't the average the same as the median? In which case, isn't that the 50% point? So half of the people will always be less than it. But when you phrase it that way, it sounds kind of depressing. Here's another useless piece of information. Do you know that half of all accidents were caused by the other driver? It's not a very useful piece of information, right? It sounds kind of like I'm telling you something useful, but I'm not really. So yeah, 98% of it is very impressive. It means that, only 1% of the people who took that particular test did better than you as a score. You should be proud of that. That's a good number.
Like, fat lot, that's done for me. I'm a great writer, but I can't make any money at it.
That's like being a great musician. Most of them work in McDonald's.
Also, I'm a great musician. I play all kinds of instruments. Just like,
okay.
But if you ask me, have I told my kids they should go into the arts? I say no, go into the sciences. That's why I'm back.
Jenny, have you published any books?
I have, yeah.
Oh, what are they? What's one of them called?
What's your genre? What do you write about?
Well, what I did write about is for young adults. It's a book. I grew up in Alaska, and it's a book about a novel for like 12-year-olds about living in Alaska. And it was not a bad book, but I probably made $2 total on profit. I get like 1 cent per book. So I'm going to be a nurse so that I actually get a paycheck.
But I mean, don't give up your interest.
Yeah. I'm going to keep writing.
I think, enjoy music and enjoy writing, and if they publish it, great, and that's perfect, and you get money. But if they don't, you should still do it. And there are other. I couldn't write to save myself. I could probably write a math book, but that's it. My wife had a friend, and there was a site, I couldn't tell you its name now, but actually you just go to the site and you publish your material there, and people, you won't get paid for it, but people can donate if they like the book. And she didn't do books. She did little novel, like you could read it in 20 minutes. I don't know what you would call that, but it's a little baby story. That was her genre, and she used to do that. And she got people would comment and say how they loved that character, and could you do another, story with that character in it? And it gives you some feedback, and it's kind of fun. And I think it's just a way for you to feel that you're not just writing for yourself, but you've got at least an audience of some kind. I don't think it'd be hard to find that site. You would just do various, I'm sure there are more than one version of that site. And that may be something you could do. I'm kind of lucky. I got a job that I enjoy doing. So my job is my fun and my fun is my job. That is kind of lucky.
Well, the ironic thing was that I was so scared of doing math. I got my bachelor's of arts and managed to do it without taking any math. And finally, I just thought, I have to go back and start where I left off in high school. And here I am.
Maybe you can somehow incorporate your writing into your nursing.
I think
I'm not sure what that looks like yet, but I'm thinking about that too, since I like to play the cello. But
playing the cello and being a nurse, you're not going to be a nurse. You are going to be a nurse, Marie, aren't you?
Well, trying to be.
Trying to be. So playing the cello and being a nurse, there are certain restrictions. I wouldn't do it while you're taking their blood pressure or trying to give them an injection. I would do it as a therapy.
Yes, that's what I was thinking.
Make their life, to make their life a little bit more pleasant, right? And that would be cool. I don't think it would be such a good idea for me to visit people in hospital and do calculus with them. I would think it would be fun, but I'm not so sure the majority of them would. So my skill set is kind of restricted mostly to teaching. But yeah.
Okay, I'll let you go, and Marie, you can ask your questions, but thank you, Professor.
You're welcome.
See you
And
later.
you're enjoying stats, right? It's
I
not
love
stressing you
it.
out. Cool.
I love it. Yeah.
Right. Well, bye-bye then. Thank you.
Okay, bye.
What you got for me, Marie?
Okay, so the first one is...
Or no, if you want to hear Marie, I was going to say if you want.
There we go. Okay, so yesterday on the notes, you had a question of what age would you need to be in the bottom 23%. And I know how to calculate it, but
Did I not get the right answer?
No, you did.
Okay.
But you wrote something, you wrote P of X is less than or equal to something, and then you scratched it out.
I don't
I was
know.
confused.
Right, so what was the question, and I'll rewrite what it should say. I'll go onto my white screen.
Okay. It was mu equals 35.
Okay.
Standard deviation, or sigma, equals 15.
So we know this is about a population, okay?
Yeah.
And probably an age story.
Yes. And it was, what age would you need to be in the bottom 23%?
So it would be some like a missing number.
Oh,
right?
okay. Okay.
And so what I'm saying is that if that was 35 and the bottom 23% would be here.
You're looking for that X value.
We're trying to find that guy. So
Okay.
that's what I think the question marks were just a placeholder for what that number ends up being.
Okay, that makes sense.
And as you said, you knew how to do it. It's an inverse norm question, isn't it?
Yeah.
Right.
Okay.
What was your next one?
And the next one's on the 6.3 homework.
Okay. Do you want me to bring that one up? Is it probably hard to describe otherwise?
I'll check it really quick. I guess I could try to tell it to you. So
Okay, go for it. If it doesn't make sense, not that you're doing anything wrong, but if I'm not understanding it, I'll go in and look. But
Okay.
we'll go this way first. What you got?
Okay, so there's a company called Acrotime. It's a manufacturer of watches. And then the researchers of the company have shown that the watches have a average life of 34 months before certain electronic components deteriorate.
Right, so your watch will break in about 34 months. Not a very good watch, because I don't even
No.
get it for 3 years, but whatever, right?
And the sigma or standard deviation of the watch lifetimes is 4 months.
So,
and it's
okay.
a normal distribution.
That's cool.
Okay. And then the question is, if the company guarantees a full refund on any defective watch for 2 years after purchase, what percentage of total production will the company expect to replace?
So if you imagine 2 years is 24, and let's just say 24 is here, this is the percentage of the ones that end up failing inside the 2 year period.
Yeah.
So you're being asked to find that percentage there. So that means I'm looking for the percentage that you get X less than 24. So that's going to be a normal CDF question. Right, I know X and I know I'm looking for less than 24. And so it's going to be negative 999, which is just my placeholder for as low as you like, 24, 34, and a 4.
Okay.
So since it's there, I might as well finish it. I'm just curious myself to know. Negative 999, comma, 24, comma, 34, comma, 4. And it looks to me that they are pretty safe.
Oh, so I put in 0.06%, and I think it said I was wrong.
It's only 0.6%.
Oh, no, I put 0.6%.
Right, but I think they wanted the answer as decimals. That's all. Try it with a decimal.
They have a percent sign next to it.
Oh, then they do want this. I'll check my numbers.
Maybe they want. Oh, they said round your answer to 2 decimal places. So maybe they want a 0 after the 6, which is kind of strange.
No. Oh God, no. This guy I'm looking at is the same guy you're looking at, and if I round this off to as a percentage, I get 0.62%. Okay, so that's to 2 decimal places. And I'm assuming that they mean round off the decimal number to 2 decimal places, not the decimal to 2 decimal places. So don't do that, but do this.
Okay, let me try. I'll try submitting that. And that's right. Okay.
Okay.
Thank you.
Okay, that was an easy fix.
Okay.
Just look at this reality then. What that means to this company is that less than 1% of their watches, people complain and send them back, right?
Yeah.
So that's only because they guarantee 2 years, right? Right, that was the story. We only guarantee it for 2 years. What percentage gets back?
Yeah.
If they guaranteed it, and I just want to do this because I'm curious, for 1 year, or they guaranteed it for 3 years, let's see what would happen. This number is about 0.62%, right? We've got that one, we're happy with that one. Suppose they guaranteed it for 1 year. Do you think they're going to get more or less people sending it back? What would the logic be?
Figure more people.
So if they said 1 year, wouldn't that number turn to 12? Wouldn't that be a smaller percentage?
Oh.
Yeah, we guarantee our watches only for 1 year,
sense.
right? So I'm about to do the calculation again, if I can make my darn calculator get out of the weird mode it's in. Oh, it's not behaving. Come on, calculator. Gotcha. And I'm going to go back to that question, and I'm going to change it to 12 months. And if you do it for 12 months, you get this answer. Roughly 1.9 e to the negative 8, which is 0.00000. Oh, to heck with it. Would you agree it's virtually one person in Kansas is going to send their watch back, right?
Yeah, that makes sense because the watch will probably be fine for up to a year.
Right. I mean, if the average one lasts 34 months and the standard deviation isn't too big, you can imagine 12 months is going to be a pretty rare event, right?
Yeah.
Now, if they guaranteed it for 3 years, would you agree that that's going to increase?
Yeah. Yeah.
And it might increase to a number we don't like. And I've got a feeling it's going to increase to a number that will probably make them bankrupt. So I'm typing in the question, but now with 36. And the answer is about 69.1%, 69.14%. That is more than 2/3 of the watches would get sent back. So you can see in that case there, the company would end up paying back 2/3 of their revenue.
Yeah.
And wouldn't they also get the reputation of horrible watches? They break all the time. They don't live up to the promotion of 3 years life expectancy.
Also, that's why some companies might only want to have a 1-year warranty.
I'm sure
Yeah.
the reason is that. Because if you think about it, it's probably going to be one of these ridiculous numbers. It might not be as small as that. It might be 0.1%, which means only 1 in 1,000 watches ever get sent back. And they're also relying on people's laziness. Do you know if you have a watch for 11 months and it's only meant to last you a year, do you know you probably think it's not worth the trouble? Plus you have to find your receipt or all those, the little things that they catch you on that you never keep. So a 1-year warranty is probably the safest warranty that you could probably do if you're a company, as long as your mean is at least bigger than 12 months, right? You got to make sure that's true, just so that this percentage doesn't become. Some people do, some companies choose to be on the side of safety just so that they get a good reputation. Can you imagine a different company that made their watches really well and they got an average of 82, right? It was a big chunk of time. Do you know they might only give you a 5-year warranty, which is only 60 months? But the reason they'll give you a 5-year warranty, won't it end up being one of these numbers? Virtually nobody's watch will break in under 5 years. So they get a really good reputation with a really good warranty on it.
Because it's,
so
because the warranty is less than the mean.
Yeah, and
okay.
Safely less than the mean, right?
Yeah.
If the mean was 62, do not do that as your warranty.
No.
You can imagine, half your 40% of your watches are probably not going to make it, right? And you're going to get a bad reputation, and you end up paying back a lot of money, and that's not good business. So it's that's where that came from.